lesson is about limiting reactants. So you are going to need your periodic table, some background knowledge on stoichiometry, and of course, your pencil and the calculator. So let's think about a chemical reaction here where I have lithium plus oxygen to make lithium oxide. When we have a balanced equation and I have 4 lithiums on the left, 4 lithiums on the right, 2 oxygens on the left, and 2 oxygens on the right. If we have 804 grams of lithium available for the reaction, calculate the amount of oxygen in grams you will need to pump into the reaction to ensure that all of the lithium reacts. Our starting point is going to be that we are starting with 804 grams of lithium, and we know that whenever we have grams, grams needs to go to moles. So we need to look at our periodic table to see the molar mass of lithium, 6.941 grams of lithium and 1 mole of lithium. That will cancel out my grams. We know that if their units are diagonal from each other, they cancel out. So I now have moles of lithium. Once I have moles of lithium, what do I want to get to? Well, it wants me to calculate the amount of oxygen in grams. In order to get there, I need to get to moles of oxygen. I need to compare moles of lithium to moles of oxygen. And that is a 4-to-1 ratio or a 1-to-4 ratio, however you're looking at it. And we need to look at it as far as, since I have moles of lithium on top here, my moles of lithium needs to be on the bottom. So that 4 from here, the coefficient needs to be on the bottom to cancel out my moles of lithium. Therefore, my moles of oxygen is on top. This leaves us with just one more step because I ultimately want the amount of oxygen in grams. So what I want grams of oxygen. I've got moles of oxygen. So that last piece, and now this is diatomic oxygen. So I need to look at my periodic table, and we know that there's 16 grams in 1 mole of just O, but we have O2, so we got to double that to 32. And when we do this math, and we multiply all the way across, we multiply all the way across the bottom, and then we do total top divided by total bottom, we get, with 3 significant figures, 927 grams of oxygen. Good, hopefully that's review. So far, we've assumed that all of the reactants taking part in the reaction have been transformed into products. There isn't any leftovers. But this is not usually the case. This scene is from The Father of the Bride, and it really helps to kind of show limiting versus excess reactants.
Nina said as long as I was escaping, would I mind escaping to the market and picking up something for dinner? Sure, that was all I needed. A busy supermarket. I needed to drive, mellow out, get my mind off the wedding. But mellowing out was not in the cards.
Yeah.
Well, I got a real nice bit of land here.
Excuse me, sir. What are you doing?
I'll tell you what I'm doing. I want to buy 8 hot dogs and 8 hot dog buns to go with them. But no one sells 8 hot dog buns. They only sell 12 hot dog buns. So I end up paying for 4 buns I don't need. So I am removing the superfluous buns.
I'm sorry, sir, but you're going to have to pay for all 12 buns. They're not marked individually.
Yeah. You want to know why? Because some big shot over at the Wiener Company got together with some big shot over at the Bun Company and decided to rip off the American public. Because they think the American public is a bunch of trusting nitwits who'll pay for things they don't need rather than make a stink. Well, they're not ripping off this nitwit anymore because I'm not paying for one more thing I don't need. George Banks is saying no.
Who's George Banks?
Me! Why don't we just calm down now, sir? I'll tell you why we don't calm down. Because you're not excited. It takes 2 people for a we to calm down, doesn't it?
That I don't know, sir. I'm just the assistant manager of a supermarket. But I'll tell you this. If you don't pipe down and pay for those buns, I'm going to call the police.
Oh, right. Yeah. Yeah, right. That's right. Hey, right. Hey. Hey, come here. Come here. Come here. That was the low point. Flipping out over 4 hot dog buns.
So interestingly, if you were to buy one package of hot dogs and one package of hot dog buns, if there are 8 hot dogs and 10 hot dog buns, we will be limited to only make 8 hot dogs, and we would have an excess of buns. We would have 2 left over. So that just kind of gives us an idea of if I have different amounts of reactants, what that limits us to in a chemical reaction. Let's think about a grilled cheese. Let's say that it takes bread and cheese to make a grilled cheese goodness sandwich. And if I were to think a little bit more like a chemical reaction is set up, it takes 2 pieces of bread and 1 piece of cheese to make 1 grilled cheese sandwich, which a grilled cheese sandwich as a unit would be 2 pieces of bread and 1 cheese, so B2C. All right, so let's say that I have 3, 6, 7, 8 pieces of bread and 3 pieces of cheese. Well, so I gotta take my 1 cheese and 2 breads and make 1 of those grilled cheese sandwiches. Take another piece of cheese and 2 more pieces of bread to make another grilled cheese sandwich. And the last piece of cheese and 2 pieces of bread to make a 3rd sandwich. So if we think about this, what is my limiting reactant? What is my excess reactant? How much product can I make based on my limiting reactant and excess reactant? What reactant did we have excess of? The bread, right? I have 2 pieces of bread left over. So therefore we call it the excess reactant. What product did we run out of that limited our sandwich production? Well, the cheese. So the cheese is then called our limiting reactant. Let's say I had 100 pieces of bread, 30 slices of cheese. How many sandwiches could I make? Could I make 100 sandwiches? Could I make 130 sandwiches? 80, 50, 30, or am I not given enough information? Think about that. Well, we just said that I was limited by my cheese. And so if I had 30 slices of cheese, I should be able to make 30 sandwiches. Because this is a 1-to-1 ratio. If I have 30 slices of cheese, I can make 30 sandwiches. So limiting reactants is the reactant that is completely consumed in a chemical reaction. It determines or it limits the amount of product that's formed. Let's think of this question. How many moles of water can we make from 6 moles of hydrogen and 4 moles of oxygen? Let's look at this balanced equation. Hydrogen plus oxygen yields H2O. So when we balance this, I have 4 H's on the right, 4 H's on the left, 2 O's on the left, 2 O's on the right. You've got to make sure that we're balanced. So we look at what we're starting with. I have 6 moles of hydrogen, 6 moles of H2, 4 moles of oxygen, 4 moles of O2. Whenever I'm given moles of one thing, and especially here, I want to know moles of water. So what do I want? Moles of water. What have I got? Moles of hydrogen. So I need to look at this ratio. Water, what do I want? Moles of water. And there are 2 moles of water for every 2 moles of hydrogen. Same for this next one. I have moles of oxygen. What do I want? I want moles of water. So that's 2 moles of water for every 1 mole of oxygen. If we do this, 6 times 2 is 12, divided by 2 is 6. 4 times 2 is 8, divided by 1 is 8. Let's think about this. And how many moles of water can I actually make? Can I make 6 or can I make 8? Well, I only have enough hydrogen to make 6. I can't make 8 if I am limited by the hydrogen, the amount of hydrogen. If I had 4 moles of oxygen to make 8 moles of water, but I can't because I only have enough hydrogen to make 6 moles of water. So I would have extra oxygen left over, kind of like the bread. If I went back to look at this one, I've got 100 pieces of bread, so that should allow me to make 50 grilled cheese sandwiches, but I can't make 50 if I only have enough cheese to make 30. What about this one? What mass of iron in grams can be formed from 113 grams of aluminum and 279 grams of iron 3 oxide? Hopefully you're seeing by now that I have to start two problems because I'm given two amounts of reactants. First, I need to actually write the equation if it isn't actually written. So we would say aluminum plus Fe2O3 yields, and this is a single replacement reaction. So aluminum is a metal, it's going to kick out the metal iron. So Al2O3, and iron will be by itself. And once we balance it, we can see our mole ratios. So I have grams of aluminum, I need to get to moles of aluminum. Same with down here, I have grams of Fe2O3, I need to find that molar mass of Fe2O3 for every 1 mole of Fe2O3. The next we need to look at, we're hopping from moles of aluminum to, we want to know, mass of iron. So we need to get to this product, iron. So we need to compare aluminum, moles of aluminum to moles of iron. And that's a 2 to 2 ratio. Same at the bottom, we need to compare Fe2O3, which is a 1 mole of Fe2O3 for every 2 moles of iron. Okay, one more step because we want to get to mass of iron. Right now, both of these are at moles of iron. So our last step is finding the molar mass of just Fe. So we went from grams of aluminum to moles of aluminum to moles of iron to grams of iron. Down here, similarly, I went from grams of Fe2O3 to moles of Fe2O3, moles of Fe2O3 to moles of iron, and then moles of iron to grams of iron. When we go through and do all this math, if I have this much aluminum, it will produce 234 grams of iron. If I have this much iron oxide, it will produce this much grams of iron. So what am I limited by? Can I create 234 or can I create 195? I can only create 195. This is my limiting reactant. Reactant, again, is not this. It is my Fe2O3 as the reactant, right? Reactants are on the left. The reactant that I have excess of would be my aluminum. Now, what if I asked how much excess is there? So if we were to think about our grilled cheese sandwich analogy, I can create 3 sandwiches. 3 sandwiches, I need to think back to if I said, okay, well, I have 3 pieces of cheese that I'm going to be using, so that requires that I have 6 pieces of bread. I need to think back, take my reactant, my limiting reactant, and go, okay, if I use all of my limiting reactant, how much of the other reactant do I need to use? Well, 3 pieces of cheese, so that would be 3 C's times 2 breads over 1 cheese. I need to look at this ratio from a reactant to reactant. Well, 3 times 2 is 6. So I would go, okay, 1, 2, 3, 4, 5, 6. It requires 6. I started with 8, so then we subtract. What am I starting with? 8 minus what do I actually consume? 6. So I would have 2 pieces left over. Now let's figure out how much excess there is. We said just a second ago that our limiting reactant was our Fe2O3. So I need to start with my 279 grams of Fe2O3 because that is my limiting reactant. So number 1, start with limiting reactant. Then I need to get to, if I am in grams of my limiting reactant and I was told how many grams of my other reactant, I need to get to grams of the other reactant. So number 2, go to grams of other reactant. We already found how much yield I can create. In that last slide, we said we can only create 195 grams of iron. So we're starting with our limiting reactant, and we're actually going to see how much aluminum we actually need. We don't need all 113 grams of it. If I have grams of Fe2O3, I need to get to moles of Fe2O3. And we have, even from that last slide, we already figured out that there is 159.70 grams of Fe2O3 in 1 mole of Fe2O3. The only thing we haven't compared, though, is our mole to mole ratio of Fe2O3 to aluminum. And if you go back to that slide that has our equation on it, it's 2 aluminum plus 1 Fe2O3 combined to create Al2O3 plus 2 Fe. This was our reaction that we're working with. So when I want to go from, I told you I'm starting here, and I want to go to the other reactant. So here I have 1 mole, and they have to be diagonal, remember to cancel those units. 1 mole of Fe2O3 to every 2 moles of aluminum. And then finally, so I've gone grams to moles, moles to moles. I want to see how many grams of aluminum I actually need. So for every 1 mole of aluminum, we already looked, and there's 26.98 grams of aluminum. So here's where you need to get your calculator out. And we're going to do our 279 times 1 times 2 times 26.98. And all divided by 159.70 times 1 times 1 is 159.70. So we only need 94.27 grams of aluminum to use up all of our iron 3 oxide. We only need 94.27 grams of aluminum. So we have step number 1. We started with our limiting reactant. Number 2, we went 2 grams of the other reactant to see how much we actually needed to make it happen. Number 3, now we subtract. How much aluminum did we start with? 113 grams. How much do we actually use? And we'll go to 3 sig figs here. We'll round this up to 3, 94.3 minus 94.3 grams of aluminum. And when we do that, 113 minus 94.3, I get 18.7 grams of aluminum that is left over, or we can say in excess. So let's wrap this up by doing a practice problem here. Why don't you pause the video and try to work this problem out. Given 50 grams of potassium hydroxide and 20 grams of phosphoric acid, how many grams of K3PO4 potassium phosphate can be prepared? Which reactant is the limiting reagent? Which is the excess? And how much excess is there? So why don't you try pausing the video here and working through it, similar to how we did the last problem, and then we'll go over it together in a minute. All right, hopefully you've had the chance to get an answer here. So I'm going to start up and say I've got 50 grams of KOH, and then down here, 20 grams of H3PO4. I always like to double check to make sure that my equation is balanced. And it looks like 6 H's, 6 H's, 3 K's, 3 K's. We look good. So first, I'm going to go from grams of both of these to moles of both of them. And I just found the molar mass of all of these compounds. So KOH, I'm going to have grams on the bottom. It's molar mass, so the 56.105 grams for 1 mole of KOH. Make sure that you are labeling. Down here, my H3PO4, I found that there was 97.998 grams for 1 mole of that. Now I am at moles of both of my reactants. I want to see how many grams of this product, K3PO4. So right now I'm going from each reactant to product, reactant to product, same product. So I need to compare my mole to mole ratio for both of these reactants. So when looking at KOH, I have 3 moles of KOH for 1 mole of K3PO4. So my moles of KOH have to be down here. There's 3 moles KOH for 1 mole K3PO4. Down here, I'm going to compare, I have 1 mole of H3PO4 to 1 mole of K3PO4. So it's a 1-to-1 ratio. H3PO4 needs to be on the bottom to cancel out. Now for both of these last steps, I want to get to, I'm at moles of K3PO4. And we just got to get to grams of K3PO4. So we have the same last chunk. So for 1 mole, we're just going to use the molar mass. K3PO4 is 212.268 grams. And then I do like to go back and check to make sure everything cancels. Grams of KOH cancels. Moles and moles of KOH cancel. Moles and moles of K3PO4. I'm going to be left with grams of K3PO4. Here, grams and grams of H3PO4. Moles and moles of H3PO4. Moles and moles of K3PO4. And again, I'm left with grams of potassium phosphate. So now we just need to get our calculator out, and I need to multiply across. So 50 times 1 times 1 times 212.268. You need to divide it by 56, whatever the product of 56 times 3. So I'm going to put divided by parentheses 56.105 times 3. So it will divide it by that product. So I get 63. How many sig figs do I want? 63.1, we'll say, grams of K3PO4. And to do our second problem here, I'm going to start with 20 times 1 times 1 times 212.268, and all divided by 97.998. And I get 43.32 grams of K3PO4. So our last question is, well, for this part, so how much can I make of my product? Can I make 63 grams or can I make 43 grams? I can only make 43 grams of product, which means this must be my limiting reactant. So my first question is, how many grams of K3PO4 can be prepared? Only 43.3 grams can be prepared. What is my limiting reagent or reactant? Same thing. Is my H3PO4. I'm limited by that because I can only make 43. I can't make 63 grams. I don't have enough. I have extra KOH, so I don't have enough H3PO4 to make 63 grams. So this is my KOH. Now, how much excess is there? Remember, to find that out, think back to the steps that we just talked about. Number one, I need to start with my limiting reactant, which we said was this, 20 grams of H3PO4. So I'm going to slide back up here for a second. This time, we need to start with my limiting reactant. I'm going to write LR for limiting reactant. And I need to go, now we're not going to a product anymore. I need to go from one reactant, my limiting reactant, to the excess reactant to see how much I actually need, because I know that I have excess of it. We're starting with 20 grams, and we're going to do our very same first step here. We're going to go grams to moles, so that then we can go moles of one reactant to moles of the other reactant. So we can just use the same data, 97.998 grams for 1 mole. Next, I need to compare moles of reactant to moles of other reactant. I need to have H3PO4 on the bottom, and we see that there's a 1. And compared to my other reactant that I know that there's excess of, 3. Now, because my KOH was originally given to me in grams, I know I started with 50 grams. We need to go from moles to grams of KOH. So I know that for every 1 mole of KOH, we already found its molar mass, 56.105. So we can see here, I'm going to be left with grams of KOH, which is great because I know I started with 50 grams. So let's see how much KOH I actually use in this reaction when I use up all of my H3PO4. So I'm going to start with 20 grams times 1 times 3 times 56.105, and all divided by 97.998 times 1 is 34.4 grams of KOH used. Well, it didn't ask me how much KOH is used. It says how much excess is there. Well, I know that I used, to use up all of my H3PO4 reactant, it used 34.4 grams of KOH. I started with 50 grams of KOH. I used 34.4 grams of KOH. So let's just subtract that to see how much excess or extra there was. 50 minus 34.4, we have 15.6 grams KOH in excess. Great work, everyone. To sum up what we just did about limiting reactants, When there are two or more reactants in some cases, there's an insufficient amount of one reactant to consume the other reactants completely. The reactant that is in short supply limits the quantity of product that can be formed. The theoretical yield of products is limited by this limiting reactant. In our prior examples, we were given grams of reactants and asked to find grams of product. But sometimes you don't even have to go that far. In this sample problem, ammonia is prepared by the following reaction. If you mix 10 moles of nitrogen, 25 moles of hydrogen, what is the limiting reactant? So in this case, we're going to start with, we're given quantity of both reactants. So instead of starting with grams, we're already at moles with both of these. So why don't you pause and see if you can work to find what the limiting reactant is. Is it the nitrogen or is it the hydrogen? Let's see if you set it up right. We started with 10 moles of N2 and 25 moles of H2. Since we're already at moles of reactant, we need to get to moles of product. So let's compare my ratio of N2 to product. So 1 mole of N2, which would be down here, because I need my units to be diagonal from each other. 2 moles of my product, NH3. And for here, I need to compare my moles of H2 to moles of product. So I will have 3 moles of H2 for every 2 moles of NH3. Let's do 10 times 2 is 20 divided by 1 is 20 moles of NH3 as compared to, let's do this, 25 times 2 is 50. 50 divided by 3, let's see what that gives us. 50 divided by 3, 16.7 moles of NH3. So then we have to ask ourselves, do we have enough reactants to make 20 moles of product or 16.7 moles of product? We can only do 16.7, so we must be limited by my hydrogen. That was a much quicker way to find the limiting reactant when you have to start with grams and finish with grams. It's that 2 extra steps. How about this one? Why don't you pause for a minute and see what the limiting reactant is in this problem. Let's see if we got the same answer. And also, here's part 2. The same question. So I want you to figure out what is the limiting reactant and how much Fe will be produced. So let's set this up, both finding the same thing that we want to find. Since we want to get to, you could choose, since we're given amount of this reactant and amount of this reactant. When we're looking at our first problem, it says, what's the limiting reactant? Well, it didn't tell us which product to find. You could have gone from moles of iron oxide, iron 3 oxide, and carbon monoxide to either product and compared to see which one your limiting reactant is. However, if we're actually asked how much Fe is produced, I am going to just use that as my final end product. So let's see, 5 moles of CO. So I want to compare Fe2O3, 1 mole of that, 2 moles of Fe. And I'm going to compare my 3 moles of carbon monoxide to every 2 moles of Fe. 25 times 2 will have 50 moles of iron produced from my iron 3 oxide. And let's see how much for my carbon monoxide. 65 times 2 divided by 3, 43.3 moles. So you tell me, of these answers, how much iron will be produced? Well, hopefully you realize that it's only 43 moles can be produced. And therefore, what's my limiting reactant? It's the reactant that produced that 43. So it should be my carbon monoxide.